Good morning and welcome to the Calculus Reading Group. Each week, we invite researchers in machine learning and software engineering to present and discuss their work on calculus. Today, I am pleased to introduce Jacques, an alumnus of the University of Montreal and now professor at McMaster University in Ontario. Bonjour et bienvenue dans le groupe de lecture de calcul. Chaque semaine, nous invitons des chercheurs en apprentissage automatique et ingénieurs logiciels à présenter et à discuter de leurs travaux sur le calcul. Aujourd'hui, j'ai le plaisir de vous présenter Jacques, ancien élève de l'Université de Montréal et maintenant professeur à l'Université McMaster en Ontario. Professor Carrette has kindly accepted our invitation to speak about his recent work on Drasil, a system for knowledge-based program synthesis. More broadly, Professor Carrette's research focuses on computational mathematics. He has published extensively on probabilistic programming, type theory, and metaprogramming in the Haskell language. Le professeur Carrette a aimablement accepté notre invitation à parler de ses récents travaux sur Drasil, un système de synthèse de programmes axés sur les connaissances. Plus généralement, ses recherches portent sur la mathématique computationnelle. Il a publié des travaux sur le calcul probabiliste, la théorie des types et la métaprogrammation du langage Haskell. Without further ado, may I invite you to please join me in giving a very warm welcome to Professor Carrette. Veuillez vous joindre à moi pour souhaiter chaleureusement la bienvenue au Professeur Carrette.
Merci. I'm going to give the talk in English, mais je peux répondre à toutes les questions en français si vous voulez. So I'm going to talk about Drasil, and I'm going to first start by where it comes from, because it comes from, as the title says, a confluence of various ideas that kind of collided together that then sort of generated, pun intended, this project. So I'm going to start from some observations that I will then weave together and show how this sort of ends up at Drasil. And the four big observations is generative technologies that currently exist are good. And this is an obvious observation that there's all sorts of different kinds of software, but this has non-trivial consequences. So I'm going to dig into that observation some more to understand what that means. One of the things to understand is software is not just code. There's a lot more to software, and one really wants to look at software as a whole, not just the code, no matter how much programmers would prefer to ignore documentation. And productivity is a big deal, and understanding productivity actually helps to understand where some of the other parts go. So I'm going to actually spend a little bit of time on all four of these things because understanding them a little bit better helps understand where Drasil comes from. So on generative technologies, of course, I could spend a whole talk just on that. And here I'm going to be immodest and only talk about my work. Mostly because mine is in some sense it's kind of an oddball in the sense in that I specialize in typed code generation. And you can do that, like typed template Haskell is quite recent. MetaCaml is less recent, but almost everybody who does metaprogramming in one way, shape, or another does it either in that most fantastic system called Racket, which is entirely untyped, or in C++, which we don't talk about. And in other places, but like typed adds quite a lot of different things. But once you start really looking at how you can do this, you get a feel for all the sorts of things that you can generate. So I won't talk about all of these things. I'm mostly saying, as far as I'm concerned, I've been working on generation of stuff for 16 years now. This is sort of, I know how to do this stuff. It's easy as far for me, so I'm kind of looking to apply it to other places, including like some of my recent work where I'm generating theory. So I'm generating AGDA and I'm generating mean from other things, because, you know, writing AGDA by hand is too easy. Why don't we tell a computer how to do it instead? If you've ever used AGDA or Lean, this would be funny. Right. So I'm going to spend a little bit more time on different kinds of software because there's lessons to learn there. So if you're going to write a one-off script, you just write it. Like there's very little software engineering process, and you should be using a spiral process to write your 10-line script of code. It's like that's a complete waste of time. But it's useful to understand that there are things that we should just write. But at the other end of the spectrum, if you're writing software that's going to go into a pacemaker that goes into a human being, you should be spending an enormous amount of time designing, and you should be legally liable for bugs in your code. So this is at the absolute opposite end of the spectrum, where the software engineering process that you should be using should be quite extreme. Operating system for a probe like Voyager should be kind of the same, because the round trip time is so long that you can't patch that live. It's a very different process that you should look at. It's again design, but of a different kind. But and I picked Uber here, but any project which was really creating a new market, a new idea. This is like Agile is perfect for this, because basically the people on the project are talented programmers, so they know what they're doing, but their requirements, on the other hand, are completely unknown. So from that point of view, they don't have no clue what they're doing. Like they're talented programmers who have no idea what they're going to do because it's changing all the time. So here, Agile is a perfect process. The Linux kernel uses slightly different ideas, where it is an enormous, and the most enormous that we know of, program family. The Linux kernel is not one program. It's hundreds of thousands of programs all mashed together. And this is an interesting idea where you've got knobs that you can turn that design a new program out of the one. We also, like some of you know about DSLs, and because I like games, there's a program called Inform 7 to create interactive fiction. And it's a DSL for creating new games that are text-based, but it's a different level of thought, where the process ends up being different. In some sense, we're back to just write it, because the necessary abstractions for doing the work have already been encoded into this DSL, so you don't have to write low-level programs anymore. And then the place where I'm going to spend the most time thinking about is research software based on math of one kind or another, but people have a research idea to do, and okay, so how do you do that? The thing about research software is it really calls for a mixture of many of these things, because part of research software is based on really well-known theory, that is well understood. And so that's like very, very solid ground. And then they're trying to do something new on top of that. So there's a mixture of both. And so we kind of want to leverage the fact that there's this really large known base on which you're trying to do something new. And so the new part can be done, say, agile, we know that. But the big, well-known stuff, like, oh, DSL's program family, lots of design, yep, absolutely, we can do that. So there's a mixture of things that can happen at the same time. So we've coined this word Softifacts for software artifact, because software artifact is too long, so we mash it up. And there's a lot of different things in a piece of software. You go on GitHub and you'll find way more than just code, right? Makefiles, installation docs, your README. You won't barely find any design or requirements documents on GitHub. It's really sad. In companies, you do. User-facing documentation, lots and lots of tests. And because I'm looking mostly at research software, there's frequently something called a theory manual. Sometimes it's a textbook or 20 textbooks, and it's referenced in some of the documentation. But whether the theory manual is clearly laid out or implicit, it kind of exists. And this is kind of interesting. Perhaps the key observation on software here is that even though a makefile and code and the documentation look very different from the outside, they're actually about the same thing. They're different views of the same information. So in many, many ways, they're highly redundant. And this is why most programmers hate writing documentation, because they hate repeating themselves. And they understand very deeply that this is pointless because they're going to get out of sync, because it's the same information. And so this is like really maddening. And it's a reason why, it's a good reason why people don't want to do it. And of course, the counterfactual way of looking at it is, if it wasn't related information, why are they all stuck together in the same place? They have to be deeply related. And like, if you look at any piece of software out there, look at their GitHub repo, there is no random junk in there, pretty much, right? So there is some deep information going on here. And so what we're going to call Softifacts are different representations of some core knowledge. So what I want to say is all of these things are actually views from the database point of view, of like, somehow there's information that is splayed out in each one of these files for different purposes. And this is now what we kind of like to do from a generative point of view. If we could figure out what that knowledge is, then it's a translation process from knowledge to the actual artifacts. And this is part of the underlying thinking going on. And lastly, the fourth component is programmer productivity. One of the reasons why most work on programmer productivity seems to fail is that it arises out of work that was basically based on manufacturing that has a very short time frame. And programmer productivity is something that doesn't happen over, if you look at what a programmer does over one day, you won't be able to tell if they're being productive or not. If you look at what they've done in the last year, yes, you might actually be able to tell that they had a productive year. And the lifespan of most software is quite long as well. And so productivity is something that needs to be looked at much longer timescales than is traditionally done at. And it becomes a lot clearer when you look at longer timescales. And one of the huge things, so if you start looking at software at the 10-year timescale and more, because there's huge amount. I worked on software that was like first born in 1980. So it's now 41 years old. The amount of uncaptured knowledge, of tacit information that the original programmers didn't write down, that was then needed to be reconstructed. And then that turned out to be false because it was true in 1983 when computers were massively slow, and is now entirely false, and therefore is a design decision that could be changed. It's a huge thing. And when you've got like enormous corporations like Google and so on and so forth, onboarding new people to tell them, here's all the tacit information is a big, big deal. And so productivity is highly related to how available is all of this information. And the flip side of productivity is if you spend 10 years designing something that you never release, you may have learned a whole lot of stuff, but it's completely pointless because nobody has ever benefited at all from your stuff. So big design up front is also a massive mistake because you're not creating value to anybody. Agile is kind of the other extreme where you're trying to maximize usefulness as quickly as possible. But if you don't capture what you're doing, then actually bringing somebody new to help things can make things much, much worse. So it's kind of a balance between these two things that is really important as far as long-term productivity in a software engineering context. And so I didn't want to write down the math, but basically productivity is still output over input. Your input is effort, and the output, this is where something is new, is over time, given all the classes of users that you're trying to please, you know, how satisfied are they versus how much knowledge you've created is kind of a reasonable measure of productivity. And it's very important to make it over time, both over the past and over the long future, to predict what you want to do, because that's how, you know, things kind of work out the best. So this is sort of the background understanding, sort of the philosophy that goes into Drasil. So we have our 4 ingredients: generative technology, software, Softifacts, and productivity. And of course, there's a lot of stuff out there that combines some of these already. So the Linux kernel does use lots of generative technologies. There's some really cool projects like Atlas and Spiral. Spiral is fantastic for digital signal processing that really is very, very strong on generation and generates a bunch of different stuff. If you take a look at all of software, then literate programming is really a tool that perfectly understands that documentation and code are things that belong together as opposed to belonging separately. And you know, there's some really core ideas in literate programming that are interesting to leverage. And org mode deals with that as well. On the flip side, you know, AutoConf, CMake, and Nixt also have different views on software as a whole and how to get there instead of this dumb ways, you know, traditionally it's done. If you really start to look at programmer productivity and generative technologies, well, you end up with a lot of DSLs. And when you really look at it, so in some of my work, when you pile things up, what happens is design choices become actually first-class artifacts that you can see in your code. And this is why I find a lot of this so interesting, where finally some of the things that used to be tacit knowledge can be captured in code through generative technology. So like, as an example, in a Linux kernel, like when you compile one from scratch, you make a whole bunch of choices. These are your design choices that you've made for, I want this kernel. So Alan K. Viewpoints for a while did some really, really cool work about thinking about this really, really deeply. Even though he's known as an OO guy, his notion of OO is way saner than almost every other notion of OO. And even though I don't like OO, I think Alan Kay has done a lot of really brilliant work, and his stuff at Viewpoints, especially his work on DSLs, is undervalued. And I'm a Haskell guy, selling the work of somebody who's known as the OO guy. I don't actually know any work that combines 2 and 3, and then there's other stuff. But it's actually quite interesting to start to look at things like the various combinations where out there you do find generated documentations. Anyway, I don't want to spend too much time on that. So let's go to Drasil. So what I'm going to do now is stop sharing the slides and start sharing something else. To go out of full screen and share this screen instead. Right. Hopefully that worked. You can.
Yeah, I can see the GitHub page now.
Right. So I made it bigger. Like I've got a huge screen, so that's sometimes a problem. So is the font okay for others? All right.
I can see it pretty well.
So the right. So this is the Drasil repo, and I'm going to sort of. I'm not going to read this per se, but I do have some notes of what I want to cover. So I'm going to put that in front of me so I can go through that. So here, like I didn't write in my slide, what is Drasil? And one of the key things, like one of the additional ingredients that was sort of implicit in this is that we only aim Drasil for well understood domains. That means that building a piece of software in that domain is science and engineering. It's not mysterious. So there are a bunch of domains where Drasil won't have a do, because it's like you really are doing something radically new, and yeah, go ahead and explore and don't look to us for help, because we need a solid foundation on which for Drasil to work. It's just kind of an important assumption. And so we've talked about duplication of knowledge across artifacts. So that's one of the things we really want to capture. That things like physics, like F equals ma, looks different in math than it does in your piece of code, yet it's the same information. And that's the thing we really want to capture. And generative technology is just a translation phase, right? If you have the right encoding of the information, then you can translate it to other formats. So domain knowledge, like physics doesn't, like solid mechanic physics hasn't changed in 100 years. It's like, so once you capture that, you're done. It's a one-time cost. Other things change a lot. So it's important to understand what are the things that you can deal with as a one-time cost, and then over the long term, you're golden. So the other parts here, artifacts are different views. The most important part are the design decisions and their rationale, and this is one of the things we're really interested in, capturing that, because that's the true information that is most hard, the hardest to see and capture. nobody ever writes that down, it seems. And there really is now a whole lot of software that is very long-lived. So there is a real market to really say, okay, like software is not a 1 year, 6 months, whatever kind of thing. Microsoft is 40 years old. I saw a tweet today where somebody actually found some code in Linux from 1979 that hasn't changed. From its original stuff. And so this is something that we need to, and we know banks have COBOL code that hasn't changed for a long time. I don't want to deal with COBOL, but still, like we should really understand that software is a different thing now, in that a lot of it lives for a long time, and we need to have processes that are able to cope with that fact. Right.
I don't know if you want to hold for questions at the end, or is it all right to?
I'm actually, especially I know, anytime. Questions are good.
Okay. Well, I was just kind of curious. So you mentioned a little bit about documentation and knowledge stored in code itself. You mentioned something about physics, F equals ma, and other types of knowledge, such as rationale, design rationales, and so just to get a clearer picture, are you targeting all these different types of knowledge, and how? Just curious, how does code synthesis fit, or you're just doing knowledge extraction, where you're kind of maybe tracing, where the knowledge comes from. But I just understand you're also trying to generate some artifacts as well, right?
So at the very top, I'm sure it says somewhere, it used to be, our tagline used to be generate everything. And oh no, there we go. Generate all the things. I've used that meme in some of my talks before. I really mean it. I want to generate everything. But I really also, at this point in time, mean generate, not synthesize. I'm not, there is no, there is one tiny bit of synthesis, and it's mostly solving. It's not true synthesis. I don't really know how to well integrate synthesis in this. So I'm everything pretty much is actively generated. Like that there is, whether you want to understand it as a program or a meta program or a meta program, there is a set of instructions that directs another program to do something, which might be generating a program, but it's programs all the way down or all the way up, or whichever way you want to look at it. At least this is the current approach.
I see. So maybe you draw a distinction between synthesis, where you're generating new knowledge rather than translating knowledge from like a domain model into some.
Synthesis would how does it fit in here? Is an interesting question, and I really don't know the answer to that. So let's go to the current generated examples. So this page and this whole website here is generated every build. So everything we're going to look at here was automatically generated. So when we change stuff, all of the stuff on here is going to change. Like even like the sentences that you read here, some of them were actually fragments of sentences that were assembled together to be displayed onto here. So we have one of the things to look at is we have some case studies, but we can, so for projectile, for example, we can generate a bunch of modules for accomplishing our task. Or we can generate one big piece of code, with no module, like one great big function. It doesn't really matter. But that also means that we need the right knobs to turn to have either view. So the knowledge needs to be done in such a way that we can know that there are logical pieces, or we can smash them all together. It can be done as a program or as a library. For different purposes, sometimes you want an API, sometimes you just want a program. One of the things that a lot of people find useful is putting in a lot of log statements so that the program that you generate outputs a lot of debug information. You can just flip a switch or more targeted, and the program like gets 10 times bigger because it's now full of debug information, and then you turn it off again. You can vary the way the inputs are taken. You can like there's other stuff that we can change. You know, do you want to use floats or doubles? Flip a switch to represent your real constants. You can do it locally. You can do it globally. It really doesn't matter very much. So we have these toggles that you can switch, we have more examples than is in the table. In the table, it only shows the example where we have code. We have stuff where the code is not spitting out, but the specification is for reasons. But let's take a look at the projectile example because it's sort of the simplest one to understand from a physics point of view. So we picked this example because it's very simple. So like think of shooting a bullet out of a cannon and where is it going to land? Is it going to hit a target? So that's simple first year problem. So here's the SRS for it. It's 28 pages long. This was 100% generated. The LaTeX for this is generated from our stuff. And so this is a generated document. At the beginning, there's some reference material. So meter, radians, and seconds. We know about all of SI, but only those three are used in this document. So this document only contains those three. Here's all the symbols that occur in the document and their units. It's really good to double check because we had mistakes. And we can just look at the table and go, hey, that's wrong. Somebody must have coded something incorrectly. As a process that looks through all of your assets and generates this table, that's very easy to program. This table would be insane for human beings to manually do. It's too much work. It'll be out of date. It'll be wrong. Never. Like there are standards for SRS that ask you to do this, and these tables are always wrong. But if you do it automatically, then they're right. Well, at least they're a true reflection of what's in the code. So we like that. Yeah, abbreviations, and then like our introduction, there's some words, blah, 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 blah. Like this whole introduction text is actually programmatically built out of pulling pieces in different places. It's almost a template, but you'll recognize that it has a structure if you look at different examples, but the specific words like projectile motion needs to be put into here. We even have a little bit of technology to get the plurals and singulars right. Right, I want to...
How much fine tuning does this require, the meta model? I mean, the typesetting is it looks fantastic.
Oh, this is like we generate LaTeX, then we generate the PDF from that.
I see. Yeah, and this is all from documentation and sources in the
yeah, I'll show you what the sources where we start from that. The picture is done. This this is not automatically generated. I'm sorry, like that is just not. But everything is cross-referenced, list the assumptions where and where the assumptions are used. These are unfortunately right now are all in English. Eventually we'd like this to be math too, but it's not right now. And then you have the models, right? We know that the acceleration is the derivative of velocity. This is all one-time cost to enter this kind of information and units and so on and so forth. Once you have all of these things, then you can start putting them together for your physics model. You can refine it to the equations that you want. I'm going to skip over that. But there's a whole bunch of this. It's all like, it displays as very long, but the actual core information is fairly small, and it's all one time. So that's shared amongst a whole lot of different softwares. So it's not that bad. Yay for LaTeX to make things pretty. Data constraints. This is fun stuff. We have typical values of most of our variables. So the position of a target, we say that in the scale of problems that we're interested in is typically around 1,000 meters. The usefulness of this is if you end up in your program and your P target is 1 millimeter, you go, what? Like, you've done something bizarre here that's not expected, and something is really weird. If it's negative, it's even like here, it's a physical constraint. We always have the target to the right. If P target ever becomes negative, you know you have a bug. Something has gone horribly, horribly wrong. So we can actually automatically generate asserts. Every time we compute P target, we can put an assert in the code that says it's positive and throw an error because this is sort of domain knowledge that can be inserted. Bigger stuff, bigger problems, this can all be used to generate not just assert, but also test cases out of this. Right. Oops.
So with these PDFs now, you mentioned a little bit about literate programming and the importance of having code and this in sync, and so what you'd like to have is maybe like a one-way generation process, or is it kind of a bi-directional where you imagine that people change some.
So right now we're very much looking at one way. Would we like two-way? Interesting. So right now, for example, we're exploring, we don't have it working, generating Jupyter notebooks for some of this. And you know, it really does mix a bunch of things, but the Jupyter notebooks don't have quite enough information to go back. So it kind of has to be one way because it's too lossy. Right. So the tables of traceability go way too far, and so let's switch to looking at the HTML view. And the reason I say it's like this has to be generated is this is the same document, but it's in HTML. It looks a little bit different, but it's all the same information. And if we scroll all the way to the end, we now see that our tables are proper. It's just that our labels are too big. And so in PDFs, they just get cut off. And of course, these kinds of tables are absolutely insane for a human being to generate, because they're just like, all of your software engineering textbooks are going to tell you you want traceability matrices, and nobody ever does it because they're a complete waste of time because they're obsolete even before you've finished doing them. But they're great because sometimes you see an X where it doesn't belong. You go, why is that dependent on that? That is just so wrong. And you go by and you realize there's a bug that it should never have depended. But yay, automation. I can actually even do this. This is generated HTML. We lay it out. So like we have a pretty printer for HTML to make sure that we can debug our own stuff so that we make sure to actually generate readable HTML because who knows, it's easy. So we go out of our way to make sure that even our generated stuff is readable. So if we go back, let's look at actual code. Right, so like the various options are laid out here. So let's look at the Python sub part. So this README is generated information, including like which version is used and like the README and everything here is generated. An example file, and I decided to pick the ones where it's one big program. And we generate a makefile, which here is almost dummy, but it lets you build the Doxygen because you've turned that on. The code is documented with author information, and this one actually has lots and lots of logging information. So you see all those prints that are automatically generated for everything and Doxygen. So some of the traceability here is like some of the information is you can see the units of each one of the inputs put into the documentation here so that you can still figure that out. If we want to look at a piece of code that is more readable, if we look at one that has been split into modules, then the calculation module, even with full documentation, is pretty short because there's not that much to calculating projectile motion. There's a lot of theory that says, this is why these, like, why should it be this formula? Well, there are reasons. And you can see it this way if you want. If you don't like Python, you know, you can look at this one in C#. Apparently that's one program, and this one has logging. Let's not do logging. So L, no L, all right, is more readable. And you know, it's the same code, right? Morally, there's no difference. People might argue bitterly that Python and C# are different, but they're like, for the purposes of this, there's no difference. So this is why it's so easy to generate these various programming languages. For this kind of code, it's all the same.
And so for this example, what would be the source or project where this was parsed from? Is this
right? So I'm gonna sort of show you that next. I'm gonna quickly go into the generated documentation because we have Doxygen. Let's not do that. Let's do Java, where you know there's some classes that have all of the usual information. So all of that stuff that we generated can then be reparsed by another tool to generate the usual stuff for your usual view of your documentation. And you know, all of this is like, there's multiple layers of generation to get to here. But it's all free once you have the base knowledge. But yes, you're absolutely right. I should be going to, how do we do this? Did I go too far?
Like there
I went
might
out
be
too far.
Question from the audience. Feel free to speak up or unmute yourself.
Sorry, can you hear me? Or
Yes.
Yes. Yeah.
oh, I thought I have like a weird headphone setup. So one question that I have is, like different programming communities might have different standards for, like, let's say documentation, and it could be that like at the end of the day, there are different standards for what goes into the code style and you know what is necessary at a company for documentation. So since we're still looking at output, I'm wondering how flexible is this DSL, is Drasil?
Well, so right now we do output a single style per programming language, but we have tried to make it as idiomatic as possible, like to make your Python look like Python and
Yeah.
so on, and like some pieces of Python will use like array slices, whereas in Java you'll have a for loop. We currently don't have as much style programmability as we'd like, but we know we want it. So it's designed to be programmable, but we only have one style.
A quick follow-up to that, is the goal to produce code that is very readable and which can be adjusted later, or is the end goal of Drasil to sort of encompass all optimizations, perhaps, and all potential things a user might want?
We're the latter. We're really not thinking that you would ever hand edit your code. We kind of see this code as low level, the same way, you know, if you're writing code in C++, how often do you go in to your assembler or your object file and tweak it? So we see this code in the same way. You kind of still want it to be readable for auditing purposes. You want to make sure that it really is what you think it should be, but it's a generated asset. And if you want to change it, you change your source. Like you change the Drasil and you regenerate, is how we're looking at it. The other problem is too hard and doesn't seem to gain enough. As far as really going the next step, we think generating everything is where you're going to get the most bang. This for sure means that you kind of need to buy into Drasil all in. It's not an incremental thing, absolutely. This is a big flaw as far as selling it to people. But I guess we're doing research, and so we're pushing, you know, this envelope to see where does it lead us.
Cool, thank you.
Right, so the obvious question of what does some of the source look like? So under Drasil data, so if we want to look at something that is the sort of, well, let's look at SI units, how they're defined. So this is a Haskell source code. So a meter is a fundamental unit, spelled meter. It's a notion of length, and its symbol is M. So unit definition, and this is all like the program doesn't know anything about any of this. You know, Candela, and all of this is the standard SI stuff. One of the things to notice perhaps is like the words. So if I were to misspell mass here, we've been really careful. Pretty sure that the word mass in all of our examples comes from here. So if we were to misspell it here, it would be misspelled everywhere. So this is by design. We call this pervasive bugs, or all bugs are shallow. If you make a small mistake, it's going to splay out absolutely everywhere, and it's going to get caught pretty much immediately because everything is going to be broken. So this is also dangerous, right? If you're a hacker and you won't go in and you make a mistake, you've now broken absolutely everything. But but it's going to get fixed equally fast. And because, you know, the knowledge, you know, of mass or kilogram is here in this one place. And then we've defined some useful stuff because, of course, second squared is used so much. So we have some combinators so that you can use s_2 and other things. What we really should do right now, this is an embedded DSL of how to define units in Haskell. It's an embedded DSL because we wanted to experiment with it. Now that it's stabilized, what we should do is de-embed it, give it an external syntax to make it pretty. But that's a different step.
Sorry, may I I have a question.
Yeah.
So I'm coming from the modeling side of everything. So
yeah.
This is the point I was waiting for, actually. So what you showed here, the SI units and the labels we use to express them, is this really knowledge or is it more data? And the reason why I'm asking is this is because the majority of the techniques in the modeling world for knowledge representation consider open world semantics, where you can say, okay, I can use kilograms to measure mass, but I can also use pounds for that, or whatever metric I want to use. So my question is this really knowledge or data? And if it's knowledge, how is this different from ontologics?
Right. So in some sense, probably it's best described as degenerate knowledge. You can easily see data as degenerate knowledge, where the amount of knowledge is quite small, and it's of a different kind. We do have a full unit system, so that you can change units, and that part can be dealt with properly, because how units work is also scientific knowledge that is known, that is more process knowledge, and that is easy to capture as well. So yes, right. And you're absolutely right that this is part of ontological data, of domain capture. We've looked at a whole lot of ontology work and found that it captures a lot of information very usefully to explain it to human beings. And as far as making it useful for operational purposes, we found it useless. We were not able, like, it just wasn't encoded in useful ways for a computer to do something meant for a computer again. So that's why we've kind of gone our own way.
Yeah, I agree completely. This is what I did my fair share on ontologies, like research-wise. I know that they have limitations, and of course, the idea is that you can integrate knowledge from different types of people or stakeholders without fixing yourself, on a certain system like SI, for example. But that requires flexibility in terms of not only the concepts, but also the relationship between the concepts. So I can say meter is A, a metric, but maybe I don't want to express it via an is a relationship, but with something else. So this is what fundamentally, distinguishes between distinguishes knowledge from data. But what I experience that this is exactly that flexibility that makes it impossible to use ontologies for practical purposes, because it is just the open world semantics will just the problem space will just explode if you want to use a moderate sized ontology for generating program code or documentation. So is this my question is this the intention here to reduce the space or reduce the complexity of the ontologies by narrowing down, let's say, the semantics of relationships?
No, well, no, like in the sense, that is not the approach we've taken at all. So the approach that we took to develop a lot of Drasil was to kind of go bottom up, because if we designed for a very long time, we would still be designing to use all of that stuff. We basically started, okay, what's the minimal amount of information in a very broad sense? What's the stuff we need to write down to make things work? And then, so internally to Drasil itself, in the first 2 years of development of Drasil, we used pure agile. We just wrote code and rewrote it and rewrote it and rewrote it until it stabilized, because we knew we didn't know what the bleep we were doing. And we had to sort of discover, and we didn't want to presume that other people's solutions, of course we knew about ontologies, would actually work or would be overkill or whatever. And so we arrived at something that is far short of ontology, not because that's what we want, but that's all we needed to get to where we are. So, well, that is an answer to your question, but perhaps not the way you
It is an answer.
expected it.
It is an answer. Actually, I really like to hear such ideas, because I mean, this is a pragmatic approach to representing knowledge, and this is exactly what's missing from certain communities. Well, in modeling at least. So yeah, I see your point, and yeah, okay, thank you.
Right. So
I think we're at the top of the hour. I don't know if you'd like to continue. I'm happy to stay, and if there are any questions as well. But please, if you need to go or if there's anything.
No, I can stay a little more. I kind of wanted to show just a bit more, and since people are interested, at least we've lost one person, but the recording is there.
Yeah. Yeah, I was wondering maybe if you could show, or I don't know if it's easy to show with the workflow how you envision a user would, or I don't know if that's something that, or
okay.
Maybe there's a tutorial that you can point towards.
Let me show here through the example. Let's still pick projectile. So I'll explain at the high level what we see the workflow as being. So typically you have a problem that you want to solve. You should know what domain that problem fits in. We have a library of information, Drasil-data. You can think of that as a database of pre-known stuff. You pull everything from that database that exists, and the rest of the information you need to encode yourself. You need to, write down the problem, write down your requirements, which are write down, and all of these things you write down, and then you basically weave together these various pieces of information with our combinators to form both your specification document and the thing that's going to become your code. That's going to generate, like to say, like these pieces of information all line up to being a solution to the problem you have. Including, we have other examples where like the model could be a differential equation that needs to be solved by an external solver. Like it's not all simple straight line code, but it's easier to show off simple straight line code. And then like we can link to external libraries to do things like solving these because that's just too much work. And it's a matter of like the first step is information aggregation, and the second step is what we call them recipes, but they're really just programs where you sequentialize all of the information that you've gathered into programs that generate the assets that you want. So like if we look at the main program for projectile, it generates the SRS from the information, it generates the website, and it generates code from a bunch of choices. And the choices here, like the base choices are, we're going to generate Python, C++, C#, Java, Swift, unmodular as a program. This is the name of the log file, full, all comments. Doxygen is going to be quiet. And if the constraints would generate warnings if they're violated, not errors, and so on. And we also generate variants documented here. And so these are the high-level switches here that you can see. So that's the very, very high level.
I see. And so it would be helpful if the user was familiar with Haskell or knew Haskell, or do you plan to offer some user interface maybe?
So the medium term, we expect to have an external DSL that would be a textual format, and then after that a UI. But right now we're still changing it too much. It would be a waste of time to create such a thing. So that right now, Drasil is for the very, very early adopters only. But we have had many first year, like who just finished their first year undergrad students, come onto our team, work on the summer, and start writing Drasil on day 2. And they didn't know Haskell. They were still able to produce stuff on their second day. So it's really not that bad.
Yeah, I mean, it looks almost like a configuration language when you kind of get into the editing.
Right.
I know some other projects. I don't know. Maybe you use Pandoc in some form, but they have some form of interfaces, command line interface or something like that for other language users. But that sounds like probably a more your focus here, if I understand, is more about the transformation about
yes.
the parsing and
yeah. So some of the work, like we have a language called GUL, which is generic object-oriented language, which is basically a DSL for object-oriented languages, from which our whole backend, generates all of those things. It's not so bad. We have a pretty printer meta language that can generate HTML, Markdown, and LaTeX. So we've got these 2 meta languages. So from there, it's actually relatively easy to do some of the stuff. And then for other things, like our assumptions, for example, the projectile motion is 2D, is almost readable. So this is kind of an English generator, but the fact that we use projectile here means that if you misspell projectile, it'll be misspelled everywhere. So whether this kind of English weaving is a good idea, we're actually gone back and forth on that several times, because this is kind of awkward to write. It's kind of template English. Yeah, if you're going to ask me, I'm not sure this is a good idea right now, but this is how it works right now to do that. But the concepts in projectile motion are all simple, like flight duration, landing point, angle, speed, position. So like here, this is a combinator for compound nouns. So launch angle, launch speed, target position. So this is all, it generates English. And then you weave them all together. So an SRS is a list of stuff, but it actually just, this one describes a document. So there's a reference section that has an introduction, table of units. I don't remember, like, this is all like, it's an embedded DSL again, but that is this here is a description of that full 28-page document that pulls information from other places to assemble it. And like we go through this document description multiple times to actually create the document, but this is sort of and of course we can move things around. I know one of my colleagues absolutely despises the fact that the reference section is at the front, but I could cut this and put it at the bottom, and that would be done.
Yeah, maybe the kind of the view can be adjusted. Like you say, it's kind of just like a projection, right? So
that's right.
It's kind of you can change that the user's preference. I'm curious, so you worked a little bit on mathematical knowledge systems. So here you're focusing a little bit more on source code to source code translation. I was wondering maybe if you think it's possible, or if this is something that others have tried, where you translate maybe from other types of artifacts like papers that have equations and so on into coders. That's something that you've foreseen in Drasil to translate from, let's say, LaTeX to code, or maybe you mentioned a little bit about that.
Yeah, I don't see it soon, because we really do need to sort of semantically mark up the information that's being put in. We need more information to know what it is. Like an equation means really very little unless you know the context in which it exists. The symbols mean very little unless you know, oh, v is velocity. It's not just v. And without that, you really, and so like a typical math document is extremely contextual. And so without accumulating all of the knowledge from the beginning, and worse, all the knowledge that's not in the document, that's assumed, it's too hard. So that's why we have to start so low level, because we kind of have to build everything up. But it's a one-time cost for most of that stuff. So that's why we're kind of hopeful.
Yeah, it's a great vision. I think if people are willing to invest in the meta programming effort and to try to kind of take a large body of maybe implicit knowledge that's been documented in different artifacts, and I think that would be fantastic. I don't know. We could maybe continue this discussion after that. I'd like to maybe put the recording. If there's any other questions from the audience, maybe there's
the audience.
I know.
Yeah, no, I think it makes sense to quit, like to stop the talk here. Yeah.
Well, I'd like to thank Professor Carrette very much for taking the time out of his schedule to speak with us today. And thanks to our for being such a good audience, Esteban, Sam, and Jason for attending, and we'll end it here. If there are any questions, you can reach out. We'll put a link to the slides, hopefully, and the website on our reading group. Thanks so much.
Yeah.